Okay, let's talk about Lewis structures. So last week we started chapter 9 a little bit talking about ionic compounds and lattice energy. But that's actually just a little tiny portion in the beginning. That's why we just lumped it in with the chapter 8 stuff. Most of what we're going to focus on in chapter 9 is drawing what we call Lewis structures. So covalent bonds. Come on, computer, you can do it. There we go. Covalent bonds, molecules, and Lewis structures. So this chapter gets a little bit hand-wavy sometimes because we've talked a bit about some of the quantum mechanical effects of what's going on here, but we didn't really get into it to the level that's really necessary to explain what's going on inside molecules. And so we're going to use some kind of older conventions for drawing molecules and for coming up with the structures. And I'm going to try to do a good job of telling you what things are actually reflect real reality and what things are just kind of shortcuts and conventions that help us out. A lot of these are context specific. So for instance, some of the structures that we draw will work really well in some contexts, but then when we start to get into electronic structure and things like that, they don't really work anymore. We need a better model. And that's just the same as quantum mechanics. Classical mechanics works well in certain situations, and then you kind of, those situations break down, like atomic spectra or something, you need a new explanation, you need a more robust theory. So the same thing's going to happen here. So let's talk a little bit about what a covalent bond is. You've probably heard of it before. How have you defined a covalent bond before? What does that mean to you? What do you think of when you think of a covalent bond? What? Two nonmetals bonding together. Yep. And what are they doing? Sharing electrons. Yeah. So that's kind of like the classic explanation of what a covalent bond is. And we'll talk about how that is or is not quite right. But it's worth at least mentioning that that's how we often think of covalent bonds. So why would electrons share, or why would atoms share electrons? Why would that happen? Yeah, you're on the right track there. So it's kind of like what we talked about last week with ionic bonds. When we have these valence electron configuration, these types of situations that these electrons are in, and we talked about how they have a special stability if they can achieve noble gas configuration, and we use that to come up with ionic charges and stuff. So another way that they can do that is by either giving or getting electrons through this sharing process that we call covalent bonding. So covalent bonding, we often think of it as, or via the Lewis model. So we'll look at the Lewis model. And the Lewis model is to say that electrons get paired up, and these atoms always try to get 8 electrons via pairing up electrons through different atoms. So if we looked at something like water, we would say, okay, if we look at each of those atoms, we could draw the atoms with their valence electrons on them. So each hydrogen would have its one valence electron. And then the oxygen would have 6. And we draw it in such a way that it shows that 2 of them are kind of missing their pair. And we would say, okay, the octet rule says that oxygen wants 8 electrons, and we know that hydrogens can't get 8 electrons because they don't have enough, or they're too small, so they only have the 1s orbital, so they can get 2 electrons. So if each hydrogen wants 2 and each oxygen wants 8, we can say, well, here's like an open space here where this atom wants an electron to be. Obviously, atoms don't actually want anything, but we can use that language sometimes to help us. And so we can say, all right, well, let's think of this like a puzzle. If we could fit these together to fill those spots together, we could make a more stable structure. And so we might draw something like this. Where those holes have been filled in by the electrons from the hydrogen. And then when we count these up, we would say, oh, okay, great. Now our oxygen has 8 electrons in its valence orbitals, because the 2 from the hydrogen are now close enough to also occupy those orbitals. And each hydrogen has the 2 electrons that it wants as well. So we can count those electrons for both atoms, because that's really what covalent means. It means in both valences at the same time. So those electrons are taking up the valence orbitals of both atoms. And that is really what a covalent bond is in reality. It is that these atoms are close enough to each other that these orbitals can actually mix. These electrons can mix and kind of be in both atoms at the same time. So that part does reflect reality. The idea of electron pairing, that electrons need to be paired up like this, doesn't quite work. We also don't often use this kind of a picture. We usually talk instead about bonds, covalent bonds, as being expressed by lines. So rather than show this way, we might draw it like this. And those lines mean something very specific. So every time we draw a line, we're specifically talking about 2 shared electrons in the Lewis model. As we get to more complicated models, we'll see that those lines don't necessarily always mean just that. And then we don't forget about those extra electrons on the oxygen. We leave those there also. And we call these things non-bonding electrons, or lone pairs. So putting together a structure that fits this octet rule, that pairs up these electrons, works well for certain classes of compounds, particularly the second row elements, especially over on the right side. So chemistry that deals primarily in those elements is served very well by this idea. And specifically, I'm thinking of organic chemistry. You go on and take organic chemistry, everything's kind of based on some of the consequences of this Lewis idea, even though we know it's not really a strong enough theory to deal with some of the more complicated stuff that comes up. But it works well in that case. So one thing we're going to look at is how to build these structures. Before we do that, we also want to look at the continuum of that sharing, which comes to something called bond polarity. So if we look at a couple different compounds, let's look at hydrogen, H2, and let's look at HF, which looks like this. And let's map the electron density inside that covalent bond. So yes, we drew a line saying that there's a covalent bond, that there's shared electrons there. But where are those electrons shared? Are they shared nice and even between the 2 atoms, or are they more like lopsided? And it turns out that in hydrogen, H2, the electrons are pretty evenly shared on the atom. If that was sort of like a graph of where the electron density is there, it's centered in the middle between the atoms, and it's kind of like pretty even. It's perfectly even across, which makes sense because they're both hydrogen atoms. If we look at HF, on the other hand, we find something very different. The electron density is not evenly distributed. Rather, it's way lopsided over on the fluorine. So the electron density is pulled more toward the fluorine. So that the electrons kind of end up occupying that space a little bit more than the other side. And that sets up a separation of charge. Electrons are negatively charged. So if they're over on the fluorine more, that means that this fluorine side is going to be kind of partially negatively charged. And because they've left behind the hydrogen side, that means the hydrogen side is going to be more positive. This is still a covalent bond. It's not ionic. But there is a little bit of separation of charge here. And so if we wrote that like this, we would say that that particular bond is a polar covalent bond. Polar meaning that there's some positive and some negative that are a little bit separated. The symbol we use for that to show that is delta plus and delta minus. So here's delta plus over on the hydrogen and delta minus over on the fluorine. Delta is the Greek letter delta is commonly used for difference. You've probably seen it in various forms. The capital delta, which is a triangle, is often used for like whole changes, and so the lowercase delta means partial, so partial positive, partial negative on that bond. All right, so where does that come from? Well, a lot of things, but more importantly to us, how do we measure it, and how do we actually know by just looking at a structure what's going on? Can we expect that kind of lopsidedness, that polar bond, or not? And the technique that we use to do that is to look at something called the electronegativity. And the electronegativity is defined as the ability of an atom to attract electrons in a chemical bond. So we're not talking about the electron affinity. We're not talking about an atom, just like a free atom grabbing an electron and becoming negative. We're saying when an atom is in a bond with another atom, what's the tendency of it to draw those electrons toward itself? And this is actually an empirical quantity. You have to measure compounds of these atoms, or either real or theoretical, and come up with these numbers. So it's this unitless number, and we'll grab a graph from the book here. Oops. All right. So there you can see some electronegativities. I don't know if you can actually read the numbers or not, but the numbers are less important. We'll look them up a couple times today. What do you see for the trend, though? Just like the other periodic trends. Where are the areas of high electronegativity? Towards the top and the right, right? So you can see, the halogen or the noble gases are totally left off this because they don't make many compounds. But the highest electronegativity element is fluorine, which means anytime fluorine's in a bond with some other atom, it's going to be drawing those electrons toward itself. And then it kind of steps down away from there. So you can see you go down by about 0.5 as you go to the left from fluorine. You drop more significantly going from the second to the third row. And then once you're kind of at the third row and down, everything kind of evens out more or less. And then again, as you get over toward the metals, you're going to get much lower electronegativities, which makes sense because we know the metals aren't attracting electrons. They tend to rather give up electrons. So the general rule of thumb here is that if we have a difference in electronegativity from 0 to 0.4, we call that nonpolar covalent. So if you have like two of the same atom, obviously the difference of electronegativity is going to be 0, whether it's hydrogen and hydrogen, oxygen, oxygen, even fluorine and fluorine. If it's an F2 molecule, yes, fluorine has the highest electronegativity, but if you got the same thing on both sides of that bond, there's no pull one direction or the other. It's just fluorine, so that's going to be a nonpolar bond. This also importantly occurs for things like CH. CH is a really common bond, and the difference between the electronegativities of carbon and hydrogen, 2.5 versus 2.1, puts you right at that 0.4 difference. So we generally say that CH bonds are nonpolar. If we are then in the 0.4 to, or let's say 0.5, just so we're not overlapping, 0.5 to 2 range, that's what we're going to call a polar covalent. And if we're greater than 2, we're going to say that's ionic. So if that difference in electronegativity exceeds 2, which it only really does between metals and nonmetals, that's saying that the pull is so great, or the difference is so great, that we're essentially transferring an electron. Right, so for instance, if you wanted to look at sodium fluoride, sodium is 0.9, fluorine is 4. So the difference between sodium 4 and 0.9 is 3.1. So we're saying that difference is so great, that's really an ionic interaction. That's no longer covalent. That's no longer shared. All right. So let's look at, so as you're working through the homework and as you're judging these things, you may want to refer back to this table at first. But ultimately we want to get to the point where we don't actually need to look up these numbers. We can mostly solve these problems of knowing whether or not a bond is going to be polar just based on the trend. Just based on saying, okay, we got like carbon and oxygen, and we know that those are like 2 apart on the periodic table, so we know oxygen being close to fluorine, that oxygen is going to pull those electrons away from carbon. So doing those kinds of judgments and remembering those trends should be all we need eventually, and we don't really need to be constantly looking up these numbers. If we're looking at more like unusual atoms, things down in the lower rows, things like that, it might be helpful to look up the numbers. But the common ones that we see all the time, hopefully we'll get to a point where we don't have to look those up anymore. All right, so we got about 10 more minutes. Let's draw some Lewis structures. So that idea that we just looked at where you kind of take the valence electrons and you pair them up, kind of like puzzle pieces, that sort of works for some compounds. But as compounds get a little bit more complicated and larger, it can kind of break down and stop working. So we need a little bit more systematic way of writing these Lewis structures, of figuring out which atoms are bound to which and how many electron pairs are doing the bonding and stuff like that. So let's do an example. If you've learned how to write Lewis structures in the past, and you have a way that works for you, then just stick with that way. But this is how I do it. You can try it this way. You can look at some different ways. You can find other ways, like on the internet or wherever too. Whatever results in you writing the right structures, or whatever you like is fine. So when I'm trying to write a Lewis structure, what I'm going to do first is calculate the total number of valence electrons. And this is where we deviate a little bit from what we did before. And the reason for that is that in a lot of compounds, the electrons don't really stay with the atom that they came with. And so we're better able to find the correct Lewis structure if we pool all the electrons first and then redistribute them as necessary. So for this one, our total valence electrons is going to be 4 from the carbon, and then 6 from each oxygen, and there's 2 of those. We can find the valence electrons. Hopefully, at this point, you can find them just by looking quickly at the periodic table and seeing that carbon's in column 4A, so 4 valence electrons. Oxygen 6A, 6 valence electrons. Those shortcuts work well for that group, that P block of elements. And so if we add that all up, we're going to get 16. Okay, so we've got our total number of electrons. Our next step then is to put down some sort of connection between the atoms, because we know the atoms have to be connected to each other. And there's a couple different ways we could do that in this case, right? You've got like, you could go COO, OCO. We could do something like this. Can anybody think of any other ways to connect those? That's all, right? All right, so which way do you think is best? The middle one? Why? Okay, why is that best? You're right. I mean, I like your intuition. You're right. Anybody know why that one's the better choice here? What? Yeah, generally these formulas are written. Whoops. Sorry. So that's going to be our better structure. Generally, these formulas are written so that the first atom is the central atom. That's not going to be true with acids, because we know with acids we always write the hydrogens first, and we know that hydrogen doesn't have enough electrons to be a central atom. It's always got to be on the outside. But other things are generally written that way. Again, this being, reflecting reality, that's not always going to work, but it's a good starting point. And hopefully we'll get to the point where that we can evaluate these Lewis structures, so that even if you would have started with one of those other ones, you would have been able to figure out, oh wait, that can't be right, and then go back to the beginning. It's okay to do some trial and error here, and we'll see why some of those other ones don't work once we get into it a little bit more. Okay, so we're going to start with that one, where we put the first atom in the center, and the other two distributed around it evenly. And then we need to fill in the rest of our electrons. So we know that each of those bonds represents 2 electrons. And we have 16 to use total. And we know that based on that octet rule that each of carbon and oxygen has to have 8 total electrons around it. So we can say, okay, we've used 4 total electrons. Everybody see the 4 that we used? So now we can start adding the rest of those 16 electrons. And we want to make sure there's 8 on each atom. So we might go, okay, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we run into a problem. You see the problem? What's the problem? The oxygen on the left has more, but that's true, and that's part of the problem. But it doesn't have to be always perfectly symmetrical. What's the actual problem here? What rule is being violated? Yeah, the oxygen on the right doesn't have enough electrons, because we said all those second row elements have to have 8 electrons around them. If we look at this oxygen, we've got 1, 2, 3, 4, 5, 6, and then 7, 8 from the bond. If we look at the carbon, we've got 1, 2, 3, 4, 5, 6, 7, 8. So those two are good. But if we look at this oxygen, we only have 1, 2, 3, 4. Not enough electrons. We don't have 8. Can we add more electrons? We can't add more electrons because we're stuck with 16. So what do we do? Any ideas? Right. So if we have the same number of electrons, but the atoms themselves don't have enough, that just means we need to share more. And sharing more means more covalent bonds. So let's get rid of some of these electrons and turn them into shared electrons instead. If I made another bond here, that would now be getting closer. And actually what turns out is you need another bond here as well. So now if we count it up, let's look at each atom first. 1, 2, 3, 4, 5, 6, 7, 8. That's good. 1, 2, 3, 4, 5, 6, 7, 8. Middle one's good. And 1, 2, 3, 4, 5, 6, 7, 8. The one on the right is good. We also want to check our overall electrons to make sure we haven't used too many or too few. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've used 16 electrons. Everything has an octet. We're good. So before you complete a structure like this, you want to check two things. One, do you have the correct total number of electrons? And then two, do your second row have 8? And we should probably put also as a corollary there, does hydrogen have 2? Because hydrogen always needs to fill 2. The atoms below the second row, which we'll get to on Thursday, don't have that restriction. So they can have more than 8. And then there's a couple other just small exceptions that we should note here. Boron gets 6. Beryllium gets 4. So those two atoms do not have enough electrons to make these, to follow the octet rule by themselves, though they're often involved in bonding where it kind of works out. But those atoms will be exceptions to the rule where they would have less than an octet. Everything else below that second row can have more expanded octets, but not really less. All right. So on Thursday, we're going to look at resonance, formal charge, and get into the shapes of atoms and molecules. Tomorrow is our spectroscopy lab. So I think it's going to be our, it's the first time we're really making like dilutions and kind of trying to do things really carefully to analyze something. We're going to be using UV-vis spectrophotometers and passing light through solutions and stuff like that. It's a fairly straightforward lab, but since we only have 3 minutes, I think we'll just wait and talk about it tomorrow. Please do try to be here on time tomorrow. I'll have your exams for you, and we will we'll try to get started right away so there's plenty of time to finish the lab, and then hopefully we'll also have time to go through the exam. So yeah, happy homeworking. Please practice these Lewis structures. That'll be a big part of what we do for the next couple chapters. I got your email.
Yeah.
I didn't respond just because I haven't graded the exam yet, so I don't.
All right.
I mean, I have pretty much by now, but the I wanted to look at yours just to like see what is going on before we talk about it. But maybe tomorrow or something when we have the exam, we can talk about it.
That's why I was going to wait until tomorrow to email you back and talk
Yeah.
to you after class.
Yeah.
All right.
I think it'll be all right.